All right, thank you very much. Sorry about that. I have Ubuntu and um, Zoom and Ubuntu have not been friends in the past like 6 months, a year, so I need to get that fixed. Okay, right. I have a lot of slides. There's a lot to tell you about, and I'm really excited to be here. So first of all, thank you for the invitation. This is my first time in GGI. Actually, this is the first time south of Lombardy. So like you guys in Italy, you guys invite me quite a bit. It's fun, but never so far south. So thank you for this opportunity. I'd love to go to Roma or Bari someday, but that's a different story. Okay, so this is also a broad audience. We literally have textbook authors, we have experimentalists. It's a broad students, in fact, so it's a broad audience. So I do want to start off with the big picture. Show lots of plots. It's not going to be 30 pages of handwritten algebra. I wouldn't be able to do that myself. But the big picture is this. And really, I give credit to Michael Peskin because I literally just ripped off the idea from his textbook some time ago, and because every time I look at the textbook, and literally not even open up the book, just look at the textbook, I start to appreciate it more and more. And the idea is that I want to talk about, it really focus on the big picture and all this stuff. Is actually the really microscopic picture. It's the fact that physical muons, in real life, they carry weak gauge charges like the electron and quarks. And what does that mean? It means that according to quantum field theory, if we were to zoom in really, really into what a muon looks like, and really, really zoom in, we start seeing that it has this wonderful structure. That you have a virtual photon that's being rated and absorbed to high orders, and if you are a little rigorous, you throw in the counter term there. But because there are weak charges, you also have pairs of neutrinos and W's that are being generated spontaneously. And what Sally Dawson and company told us back in the mid 80s is that at sufficiently high energies, these virtual states are populated. Now, this isn't, at least to me, it's not intuitive, but there are, it's not obvious, but there is some intuition. And this is the core bit of quantum field theory, is that, quantum field theory is what? It's special relativity plus quantum mechanics. Quantum mechanics is saying that physical states are superpositions of, eigenstates, or, a basis of states, including neutrinos and W's put together. They have the same quantum numbers as a muon. Special relativity is saying that these things can be off shell, and that given enough energy, then we can populate them into reality. And so this is really at the heart and core of QFT, which, Michael, probably is why you have this on your textbook. Exactly. Yeah, they opening up the book. That's only for those who are a little pathological. Anyway, so I want to give a concrete example of how this is realized in real life, and I want to go to LEP because LEP, beyond the Z program, beyond BSM searches, there is this excellent photon physics program at LEP. And this isn't to say this is the first evidence of photon structure, but it is a nice little abstract that says, here's evidence indicating the photon has partonic content. And this is a paperback from 30 years ago now. And it's really cool because it's saying that real physical particles are dressed, that for the photon, the physical photon has structure, and has many components. You can think of the photon converting through vector meson dominance to the light mesons. You have just a leading quark scattering or the emission of a gluon, or really sort of this deep and elastic sort of idea of photons scattering off of other photons. Uh, this also is a good example, I think, for this audience, because we mentioned it before that sometimes you need multiple, pieces, multiple processes to describe the same bit of data. In this case, in order to describe a hard gamma-gamma scattering at LEP, you needed 4 different pieces put together. And, these are involving different paradigms at different scales. And so inherently, resolving partonic structure is precision business. And that's the only statement I'm making about precision. So going back to the wish list, I think we're talking about on Tuesday. I forgot who was talking, but there was a discussion about wish lists and the Lazush wish list for QCD 30 years ago versus today. And if someone were to ask me, and so I'm just volunteering because of course no one's asked me, what I would want on my wish list, I would love to see in some time from now, sometime before I die, a paper appearing in the archive saying the first evidence indicating the weak boson content of a proton, a muon, a photon, whatever particle. I want to see the weak boson content of something. One, because it's cool, but also on the theory side, it actually is kind of funny because there are many theory challenges. Again, the audience is varied, so I think some of you may think, well, this is obvious, but I'm not sure all the students think that this is obvious. So this is also me trying to motivate the students to get excited about this stuff. So why is our weak bosons as partons somewhat subtle? Is that it requires putting the W and Z on the same footing as gluons and photons, which is just contrary to everyday experiences. The W's and Z's, these radiate weak decay. These have short lifetimes, whereas gluons and photons are massless. They can go on in principle for all of eternity. And so this is, trying to say that these are the same as these. um, it requires understanding the electroweak theory at high energies. And so at the technical level, it means understanding how helicity amplitudes and calculations work when you can neglect the W mass compared to the relevant energy scales. As I said already, it requires identifying and computing all contributions given order for inclusive measurements. Because now at the electroweak theory, if we're trying to do this, we have to start getting back into this business about what constitutes an inclusive measurement, what constitutes an exclusive measurement. Uh, and all exclusive measurements are inclusive to some degree, let's be honest. And more formally, it requires clarity on the degree to which what's called the collinear factorization theorem can be extended to weak bosons. And for those unfamiliar with the factorization theorem, this is the statement that says, at least for protons, that the hadronic level cross sections in proton collisions is a convolution. It's a combination of hard scattering matrix elements, PDFs, and the parton shower up to some power corrections. So in QCD for PP collisions, this is actually a somewhat rigorous theorem for Brillouin and prompt photon. And it's extended, it's applied blindly to TT bar production, all of our other favorite states. So it's not rigorously proven, but it seems to work as a pretty good paradigm. And so this is typically the starting point that we assume that this sort of formula exists for muon colliders. But okay, so what's a summary of this talk? Or what is this talk? It's a summary of a progress towards realizing this goal. I mean, this goal is not, seeing WZ PDFs in any collider is not going to be done tomorrow. However, I think there is a roadmap forming on how to achieve this realistically and so that we can see this paper appear in the archive. What this talk is that it's a lot of plots that I think a number of people have seen and have actually been shown already the past couple days, but they're my plots. So I get to actually give you the narrative and give the story and at least kind of string them all together and also give context in how this is guiding at least a few of us on how to approach things. So I want to start with this, the starting point for me. And of course, if there are any questions, just interrupt me. I will keep going until Roberto stops me. He's not even paying attention, so we're just going to continue. So the starting point for me, for us, I'm going to say let's start off with the vector boson scattering in multi-TeV muon collisions. For me, vector boson scattering, vector boson fusion, this is interchangeable. I don't care about semantics like that. What I care about is two high-energy T-channel weak, possibly electroweak bosons that are scattering into some final state F. What I like about this is that when you start getting to partonic collision scales on the order of 10 TeV, you're probing a kinematic regime in which electroweak symmetry is approximately restored. It is not restored. Electroweak symmetry is broken, but it kind of looks like broken theory, kind of. And there's a lot of work with it. It's Christian Bauer, Andrea, and Roberto, of course, along with Manohar and company. But more specifically, when the WW scattering scale starts becoming much, much larger than the W boson masses, that's when this formalism becomes a little more interesting. And again, I think, I forgot who was talking Tuesday. Was it you, Patrick, who was talking Tuesday? Someone was talking Tuesday, showing cross sections as a function of collider energy. And I want to revisit this because this tells actually a lot to, it gives a very interesting starting point. So what I'm going to be showing is a bunch of cross sections for a bunch of processes. And essentially we're comparing S-channel annihilation versus vector boson scattering. And I like vector boson scattering because the way I think about it is that it's a scattering process within a scattering process. So it's like it's a meta scattering process. So for the S-channel sort of configurations, this is something you can do at the undergraduate, graduate level intro to particle physics course. You follow your Feynman rules, you evaluate your matrix element, you square it, and you find out that the scattering rate goes like the invariant mass of the mu plus mu minus system or the collider energy. So it goes like 1 over the collider energy with some coupling power. For vector boson scattering, since it's a scattering process within a scattering process, you should be thinking about the WW invariant mass. So the vector boson scattering rate goes like 1 over the invariant mass of the WW scattering system. And then you have these log terms. And these log terms are appearing because you have more legs. And if you have more legs, 2 legs versus 4 legs in the final state, that means you have more internal propagators. So when you're doing the one-body phase space integration or n-body phase space integration over these extra lines over these propagators, that's where you're getting these logs. And so the idea is that if you go to a larger collider energy, you're going to start getting larger invariant masses. So this is parametrically suppressed, that's suppressed to a less degree, and you get these log enhancements. So the idea is collinear weak bosons are compensating for factors of a weak coupling constant. And so let's go to Higgs production, for example. Let's go to the standard model production, standard model processes, and let's start off with the Higgs. So here I'm showing cross section as a function of collider energy for Higgs plus Z, Higgs plus WW, and Higgs plus ZZ. And this is what you're seeing. You're seeing that the S-channel processes, which are the dashed lines, are going down as you increase collider energy because you have that 1 over collider energy suppression. And you see this logarithmic growth for Higgs plus Z. So let's see. So for maybe it's better to use this. For those of you in the back, you can see the red dot or no? Okay, you cannot. All right, then I'm going to go with this. Let's make it easier for people. All right, that's Higgs plus Z, Higgs WW, Higgs ZZ, and these are the vector boson scattering processes. If you were to look at the S channel, that's, for example, Higgs ZZ. That's Higgs Z going all the way down, and you just see that there's a crossover at a couple TV. Because you have 2 W's coming in. This is the full matrix element. But you're increasing the collider energy. Essentially, you're getting soft W's. So this is the soft W enhancement. This is the full matrix element. This isn't a VBF approximation. Right. Where do I see? Okay, so that's single Higgs production. What about double Higgs production? Okay, same sort of game. Here's Higgs Z, Higgs WW, Higgs ZZ. And so again, you just see characteristically, you can go to some arbitrarily large collider energy and the vector boson scattering is becoming larger. All right. Top quarks. I like top quarks. I know Jürgen likes top quarks. Many people like top quarks. What do you see for top quarks? Here's the S-channel projection for TT bar. So this is mu plus mu minus going to TT bar, and it's cratering. And here is TTH going down, but the vector boson scattering processes become dominant at a sufficiently high energy. Okay, what about 2Z, what about TT bar plus a vector? All right, so TTW is up here, TTZZ, TTZH, 4 T's, 2 T's plus 2 Higgses, and these are all the vector boson scattering processes, and here's the S channels, and they're all following below the vector boson scattering channels. One more time. The S channel processes have a smaller rate than their vector boson scattering counterparts at a sufficiently large energy. Okay, you guys are starting to notice a pattern. Let's go to supersymmetry. Let's go to very, very basic sets for supersymmetry. Let's do Chargino pairs. Here are the vector boson scattering processes. Here are the S-channel processes. There's crossover at the several TVs for various benchmarks of Chargino masses. What about stop pairs? Again, vector boson scattering is increasing compared to the S-channel processes. What about simple extensions? Simple extensions, we have singlet plus Z. Again, for different benchmark masses of a singlet mass. So this is just take the standard model, extend it by a real scalar sort of setup. So very phenomenological. You get a 400 GeV and 4 TeV, you still see the same behavior. For vector like top quark pair production, it's a little different. The crossover, so here are the S-channel rates, and here are the vector boson scattering rates, and you see that the crossover is gonna happen over here, but you still see the crossover. So this is actually a bit funny situation, but we understand what's going on here. A little different, but a lot of the same. What about many boson productions? For the chatting with the experimentalists yesterday or the day before, I like multi-boson production. I'm just a nerd like that. It's kind of fun. They're cool. Here's diboson, diboson, triboson, triboson. Here are three Higgses. Here are three Higgses plus a Z. At that point, you just can't. For triple Higgs, you just can't get this elsewhere. Not from S channel. Okay. So part of the reason why I wanted to show that whole survey is that in the past days, we've seen a plot or two, but I wanted to kind of give a picture that we came across a few years ago, that this is more universal behavior. This isn't just one or two processes. This sort of trend that vector boson scattering becomes the dominant process is rather broadly. I mean, if you go through the literature from, say, the 90s and 2000s, the papers by Dieter Zeppenfeld or Vernon Barger or Barbara Mele, you found anecdotal statements that their favorite process at the time, or the favorite process that they were studying, had this sort of behavior. But we didn't have Sherpa or Wizard or MadGraph, nor the computing resources that we have today 30, 40 papers are being written. So it was hard to do some sort of comprehensive survey looking at all these vector boson scattering processes, because I can tell you, we were the climate is not our friend when we do these sort of processes. These are very computation intensive because we're doing so many energies. There are a lot of gauge cancellations, and yeah, I don't want to know how many trees I've destroyed doing these papers. But nonetheless, let's go back to the talk and say, okay, there's now evidence. We have some pretty solid evidence that the vector boson scattering rates will always exceed S-channel rates for a given collider at a certain collider energy. Is that relationship, is that statement obvious? To me, not at first. And is there intuition for this? And actually, yes. And I want to go back to the big picture, and it's this. And so after thinking about this, hemming and hawing, it's like, yes, we know that these are the collinear logs that are giving us this enhancement. But that's a technicality thing. What's the physics behind it? And then we started thinking about this more and just taking a step back and trying to understand what happens when you start giving a parton a lot of energy. And that when you start giving a parton a lot of energy, its partonic content starts growing. And so the conjecture that we had, the idea that we had, is that, well, maybe the underlying physics is that the increasing scattering rate is simply a manifestation of the growing partonic content of a muon. We're doing this at leading order, so it's not exactly that we can, we have the all orders factorization theorem, but, is there a question? Okay. And so we thought, well, how can we how can we support evidence for this? How can we find evidence for this? And then we just thought of doing something incredibly stupid and naive. And the idea is the following: to crudely compare the rates for your final state process. Whatever is your final state that you want to compare. Whether it's ZH or singlet plus W or singlet plus Z. Let's crudely compare the rates for final state F by expressing the vector boson scattering rate in terms of the S-channel annihilation. And so the question is, oh, how do you do that? And again, it's just parametric scaling by according to kinematics, because we know for an S-channel process, it's going to go like 1 over the propagator. It's going to be proportional to the propagator, is what I mean to say. So it's going to go like 1 over the collider energy, but there's also some phase-space constraint, some phase-space closure. When your final state F has the same invariant mass as the collider energy itself, that process turns off. That's closure from phase space. And so yeah, let's just assume that the collider energy is much, much larger than the weak boson mass. Okay, fine. There's the 1 over S behavior we've been seeing and that we're familiar with. For vector boson scattering processes, we decided just let's do a naive picture of the naive application of PDF. So I'll PDF details a little more later. But this was really just the 0th order, how can we approximate this and how can we model this? And so for vector boson scattering processes, what we did was that we estimated the rate just using naive WZ PDFs. And what do I mean? I'm saying that the vector boson scattering rate is going to be this hard sub-process matrix element times the likelihood of finding a W plus in an anti-muon and a W minus in a mu minus. So these are the PDFs. And then again, we just kind of did that comparison here saying that, here's the phase space closure because as I said earlier, the kinematic scale is the invariant mass of the WW system. And so then here's the propagator. And then we just put in a mass there. We just said that the invariant mass of the W system would still be larger than the individual W mass. And then we just kind of simplified, but then we were able to kind of swap things out and write it in terms of there. Okay, so then what did we do? And this is when we started thinking about, okay, these are WPDFs, these are ZPDFs. Let's really think about what we would do if these were gluons. Let's think about this really as if it's a gluon. The gluon PDF is largest when the energy of the gluon is at its smallest. What does that mean? It becomes arbitrarily easy to radiate within a proton a gluon with arbitrarily low energy. This is just, it's easy. The gluons are massless. If my proton is 10 TeV, if my quark, my up quark is 5 TeV, 1 GeV radiation, that's simple. So, there's a 1 over Z, 1 over momentum fraction enhancement or preference. And so we just said, let's just do the crude approximation. Let's forget all the fancy stuff, the 1 minus X stuff. Let's do a crude approximation. And we plug this into here. When we do all of this stuff, the X's kind of cancel out. That's also why we did this. And what the not obvious observation was that when we went about this way, we're able to pull out this sigma S, we rewrote the vector boson scattering rate in terms of the S channel rate. The S channel rate we're able to pull out of this integral. And it turns out that this integral is solvable. I did not expect that. Turns out it is. And when you actually solve this integral, you get this very simple formula. And what is it saying? It's saying that when you choose a large enough S, that this kind of expression is greater than 1. So what are we looking at? Here's the weak coupling constant because you have a couple extra W's floating around or a couple Z's. There's a collider energy. That's the invariant mass of your final state. There's the mass of the W or Z. You can just take it to be 100 GeV or whatever you want. And when you go to a large enough S that this becomes greater than 1, then the conjecture is that your vector boson scattering rate becomes larger than your S-channel annihilation rate. Very stupid approximation. And I think the stupidest thing about this is that it worked within 10%. That was actually the moment, which scientists love. We live for those moments. So in other words, I was saying that we're able to estimate this crossover point when vector boson scattering starts to exceed the S-channel production to within 10%, which was not expected. We order of magnitude, factor 10, factor 5, that's fine. We got within 10%. And so that's kind of funny because that was saying that approximating vector boson scattering with PDFs, it actually, at these energy scales, it actually seemed to work for tree level matrix elements. And that's when we hemmed and hawed and wondered how to actually go about with this. And I remember chatting with Fabio. It's just like, this was funny. We weren't expecting that. And so, we already had wanted to look in the vector boson scattering and the effective W approximation in the context of a muon collider. But at this point, when we got this result, it was like, no, we're doing it. I'm motivated, we're motivated, so let's do it. And so we decided to then revisit the effective W approximation. In other words, weak boson parton distribution functions at leading order. And what do I mean by revisit? Because this has been studied to death. There have been so many papers. I mean, Roberto, Andrea, they have several papers on this. Jurgen's been working on this since probably I was in diapers. No offense, Jurgen. You're just kind of prolific. And you've been publishing quite early. I'm also young. Uh, and so, people have been studying this to get to death. And so what does it mean to revisit? Is that, again, if you go to the papers of Altarelli and Mele, if you look at the papers of Vernon and Tao and Dieter and all of our friends and all of these people that we trust, and you really try to compare their numbers, they don't exactly agree 100%. The qualitative behavior is the same. It's always the same, but the actual numbers. And that's because what EWA, the effective W approximation, to me, to him, to you, to her, to them, it's all slightly different, and it's all from the formulations. And you would expect qualitatively that whether or not I do an evolution by PT versus evolution by virtuality, that it shouldn't make a difference, except that it was. And so it took a while to understand this. And so, I'm not going to bore you with the details because that really was like a year's worth of, deep dive literature search during the pandemic. But, the overall idea for those unfamiliar with the effective W approximation, which I think you guys all are at this point, is that you want to treat W and Z and vector boson scattering as partons when the invariant mass of the WW system is much larger than the masses themselves. How do we go about doing this? For the muons splitting into a transversely polarized W or Z, these splitting functions are identical to the gluons in QCD. For the muon splitting into a longitudinally polarized W or Z, this is actually funny because it's a somewhat novel complication because gluons are massless. And so they don't have, when they're on shell, a longitudinal polarization. But if you dig a little more, this is not so unfamiliar to those who do photon physics, because you do have polarization of the measurements of the photon polarization when the photon is off shell. So again, you have to dig through the old QCD literature to start doing that. And one way to derive the PDFs, the electroweak PDFs, is to calculate the mu to lepton vector boson matrix element, and then just do expansion, just an honest to goodness Taylor expansion. Let's just move that here. For the transverse PDF and powers of PT over invariant mass scale, or for the longitudinal, there's also this mass over MV. That's going to come up later. W relative mass of the PT. I do answer that question. I do have slides of that. I'm just trying to think about, no, we haven't compared, didn't compare. I don't think you actually have the comparison of PT over the mass, but I don't think I have that did that expansion. I'm just, because I'm not showing everything that I wrote. I don't think I did that expansion, but there's a reason for that. I'll get to that. I think that's a good observation. Someone's following along. Well, the thing is, see, I don't think that's a good expansion, because let's suppose I go to, no, I'm going back sorry, I didn't actually catch everything you said because I was thinking while you were speaking. Yeah, but that's not necessarily, I don't buy that completely, because let's suppose we go to an EEV collider, okay? Let's go to a collider with infinite amount of energy, and then my W can have 10 TeV of energy in PT and a jillion GeV in longitudinal momentum, and it's still collinear, and the PT is still larger than the mass. So if I go to the arbitrarily large collider energies, that wouldn't work. So I'm not convinced by doing the expansion of mass over PT or PT over mass. I don't think that's a good ratio. Yes. Let me get back to this. Let me get back to this because there's an answer to this. I'm going to get to that. I will get to that. I will return to this. This is the big picture. I'll get to this in a second. I think this is the slide you want. Part of this is actually is that it's 1 and 2 splitting along an axis, and so you have here you can take mu f to be the transverse momentum if you want, or the virtuality. Yeah. All right. For the non-experts, there are several ways of doing this. The way I like to do it, just because I like working with helicity amplitudes, is that they can be obtained strictly, quite literally, from doing a Taylor expansion of the muon splitting matrix element and powers of the opening angle. And you want to go into small opening angles because this is the collinear limit. And so you quite literally take your Feynman rules, open up your favorite particle physics textbook, make sure it's one of the authors here. This way you get extra credit. You write down your current, so there's a initial state, final state, there's your polarization vector, and then you just do the expansion. The ordering that to clarify what I mean by power corrections, all that stuff, is that, at the end of the day, you get, a leading logarithmic term, but then that is a component of leading order in this collinear expansion, and then you have the higher order in the collinear expansion, and this is where other terms start showing up. Okay, the next step would then to be evaluate amplitudes for individual helicities. For example, for the longitudinal polarized W or Z, you'd want to use a longitudinal polarization vector. Now, I'm mentioning this kind of as a side remark because I heard it earlier. I'm not sure who mentioned it, who said that for the longitudinal PDF, you're selecting the Goldstone term. You actually are not selecting the Goldstone term. When the fermion current is massless, so when the muon is massless and this lepton out here is massless, this contracting with this current vanishes. So you actually are selecting out the mass over energy term. You know this. You know this. The, for massless. This is for massless. I'm glad I'm getting people excited about this. All right, so then square the matrix element. You do the one body phase space integration over the spectator lepton, and then plug into a factorization formula. All right, and this is what it looks like when you do the leading logarithmic approximation. So the leading log approximation is saying that this scale is large. So what is the scale here? So this is going back to the conversation in the chat we were having with Davida when he was giving his talk, is that the PDFs here are not renormalized. When I do this one body phase-space integration, it's over the kinematics of this final state lepton, and it's in principle, I can integrate it out to infinity. I mean, it's not really because you have only conservation of energy, a finite amount of energy, but you don't want to take the virtuality, well, okay, the virtuality of the intermediate W is related by momentum conservation to the PT of the outgoing lepton. So you can think about them, they're not equal to each other, but they're related to each other. And so you only, if you take the PT to be so large, you're taking yourself out of the collinear limit. So you just kind of plug in mu f as to be a regulator in the UV, and that's how you get it. So it looks like the RG evolve, but it's not the RG evolve PDF. And so this is a bit of distinction between what different groups of people do. Well, one subtle but important distinction is that when you're doing the evolution by virtuality versus PT of the lepton, they're related. But if you use if you use the PT, you start getting factors of 1 minus X or 1 minus Z here. And I think this is what Davida or someone else, Francesco, was showing. And actually, this can account for a lot of the differences in the literature historically. But okay, now let's plug into this factorization formula as implemented in mainstream generators. Jürgen, you can correct me when this reference is going to appear because it hasn't appeared yet, right? But the the vector boson approximation. Okay. Here, this is a upper bound on a PT. So I'm doing my phase-space integration up to some PT cutoff. So it is a it depends on what I'm computing. If I'm computing a matched calculation, sort of MLM style matching, but with the electroweak version, then in principle it shouldn't matter because that means I'm doing the +1 radiation diagram and I'm integrating from that scale. So in that case, it doesn't matter. But if I'm doing just the EWA by itself, the plots that I'm going to show you first are with taking mu f to be large on the order of the scale. But I've learned more recently why it should be taking too much smaller values. And that's kind of part of one of the takeaway messages of this talk. So I would say today, I would advocate if you don't have any other ingredients to keep mu f close to threshold for the process. For the hard scattering process, I would say keep it close to threshold. And I'm going to give you evidence for why I say that. Okay. Yes. Have I made that claim yet? I haven't given you the whole story. I'm going to show you that. Yeah. Cutting to the chase is that I'm seeing that if you go to sufficiently high energy under the right kinematic configurations, then the more complicated processes with ISR, FSR, vector boson scatterings can be well approximated below at the 10% level already by factorized contributions. So two body processes plus ISR, two body plus FSR, vector boson scattering. That's what I'm seeing at the 10% level when you include all of these. All right. Okay. So, all right, I'm running behind, so I'm going to speed up a bit. So, all right, what's the factorization formula that we're using? So PDF1, PDF2, hard scattering process, and then there are some uncertainties. So, and again, it's just something that we're familiar, and there's, I'm intentionally trying to make the parallels with PP collisions and how we deal with proton collisions, because I really see that as a guiding way forward. So you have the leading order PDFs, the bare ones, the hard scatterings. There are uncertainties from these power corrections that I showed that I'll comment on a bit. And then there's the fact that we are working without deglap evolution. Okay, so some results. All right. So we had actually a lot of fun. And so this is showing, again, cross section as a function of collider energy, going out to muon collisions of 30 TeV. So what I'm showing you on the left is vector boson scattering for all polarizations. So that means that the summing over W transverse, Z transverse, Z transverse, Z longitudinal, Z transverse, all of the configurations. And this is one particular helicity configuration that's going to the same final state. So we're kind of just, this is a component of this. And so what do you see, for example, that 4 Higgs production is not driving, is not being driven by transverse longitudinal scattering. For example, we looked at top quarks, for example. Give me 3 slides. All right, so here are top quarks. So what we see, for example, is that if you wanted to do, just TT bar production, that this is not being driven by longitudinal scattering. It's actually being driven by photon-photon scattering in this case. What about 3 bosons? Because people know that I like 3 bosons. So of course I'm going to have a 3 boson. Yeah, sure. If this is 0.210, so 20%, 10%. Oh, I mean, this is, if it's going to be for the muon, then it's going to be log of, uh, let's just say 15 TeV, 30 TeV over the electron mass, or muon mass, so large. There are also, this is being driven by photon. This specific channel, I know that this is being driven by gamma gamma, but then you would also have sizable logs that are not resummed from that are associated with the debuts. So yeah, it would be again 15 TeV over 80 GeV. Hmm? Oh, longitudinal. Oh, yeah. I'm sorry. In longitudinal, there are no logs. Yeah. Yes. Not in the leading log approximation. Yeah. So the thickness is just the thickness of the line. Oh yeah, I mean, sure. It depends on the process, because you do have some holistic configurations that are forbidden at tree level. You can't exactly, you can't exactly go to a spin. Well, you can go to spin 1, spin 0, but you have some helicity constraints. But this is being driven by logs. Yes, yes. At least the top quark one. There are other processes you deal with it on case by case basis. Okay, triboson, much of the same. Sure, sure. This is similar. This is what I meant. Yeah. It depends on the process that you're considering. That's precisely, yeah, that's what I want to say. All right. So to go on, Tova, this is going back to your question, not to put you on the spot, but you asked me whether or not there is a paper that shows how to run MATGRAPH and how to do all this stuff in MATGRAPH. There it is. So we actually, in the EWA paper, we give explicit examples and how to do the calculations, how to reproduce our stuff out of the box. And that's mostly because the different users expect different things from MadGraph out of the box, and we just can't satisfy everyone's demands. So just read the paper, and if you have any questions, just ask us. We're happy to respond. Oh, we include the photon. We include the photon. Yeah, no, we that's why it's not the effective W approximation, effective vector boson approximation, because we include the photon in there. All right, Michael, this is money plot 1, version 1. There's version 2. All right. So, right, ignore the top curve for the time being. So what I'm showing you is E plus mu minus 2 di-Higgs with 2 neutrinos. And for so that's the full matrix element, and the full matrix element is a solid line. So that's the true answer at leading order. This is the mass distribution of the di-Higgs system. So in other words, momentum conservation, WW invariant mass. The dashed line is the affected W approximation, assuming only longitudinal scattering. So in an earlier paper, we in MadGraph, we implemented polarization, being able to produce things in their helicity eigenstates and intermediate states. And so we're able to select out 2 types of processes, di-Higgs production and triple photon production. Di-Higgs is driven at like the 95% level by longitudinal scattering, triple photon by like at the 98% level by transverse scattering. The reason why that's important is that, again, if you start going through the papers by Scott Willenbrock and friends, all these areas, when they were trying to compare the effective W approximation versus full matrix element, it was a little ambiguous because the processes that they were considering were contaminated by one polarization or another. So we wanted a case in which we had a pure longitudinal scattering, and here's the case so that we can really say, this is what's going on. It's a little more control. And so you see that at large invariant masses, there's some pretty all right agreement, but then we get to smaller invariant masses. This is when the effective W approximation overestimates the full hemmed and hawed. And then we decided to have something fun. We decided to change the universe altogether. So what do I mean by that? I told Antonio, all right, this is what we need to do. We need to take the standard model electroweak Vev and reduce it by a factor of 10, but keep the couplings in their Thompson limit. The consequence is that you reduce the Z mass and the W mass by a factor of 10. Fine, ramp up the Higgs self-coupling so it stays at 125 GeV. And when we did that, that's up here. And you see, well, actually you can't see because they're overlapping, that if you were to decrease the mass by a factor of 10 consistently in the universe, then the effective W approximation and the full matrix elements, they overlap. And so what does that mean? That means that this difference here is tied to the mass. I mean, the difference is that processes occur at threshold. Exactly. Yeah, exactly. So Jürgen, the issue is that for multi-leg diagrams, underlying hard scattering processes occur always at threshold. You know, you can ramp up the LHC to be 1,000,000 times energetic. Top quarks are always produced, or almost always produced most abundantly near threshold. Yes, so if you were to increase this collider energy to be 40 TeV, you still have this threshold effect. So it's this disagreement is showing up at threshold. But at threshold is threshold. It's always this process will always start at invariant mass of 250 G. Yeah, it goes up. Yeah, fine, okay. Oh, okay, yeah, yeah, yeah. I mean, but we're shrinking it. We're shrinking it. Okay, fine. If you want to do this. Yes. Short answer is yes. But let's go through the evolution of how we conclude that. Now, how we have evidence for that statement. But, you know, back in 2021, what did we do? We also did WW3 photons. Now, I understand this plot much better now than I did then because there are artifacts here. So we did the same game. We compared uh, lepton collisions to 3 photons plus neutrinos, the full matrix element versus the effective W approximation. And then this is in the standard model with the 246 GeV VEV, and we reduced the VEV by a factor of 10, and everything just started converging. Still large uncertainties, but nonetheless we're converging. So we're saying that these disagreements here, that this disagreement from here, from let's say the central value here to this suddenly fitting in the bands, this is being tied to the mass. Okay. Same plots, just compared side by side. Yeah. I think Davida showed this very clearly. Is that it's just the law. Well, okay. Now let me take a step back. The reason is that you're actually close to threshold. So small variations of energy lead to large variations in the logarithm. Hmm? Oh, 3 photons is we required PTs of being 150 GeV. Sorry. Yeah, so we wanted something that, energetic, something that we can say, it's definitely not, collinear, but it turns out that there are collinear stuff, which uh, now but hold on, we'll go back to this because I do want to get to what you're saying. 3 photon inclusive. Uh, no, I think in retrospect, you would want to include the FSR, ISR. So, well, okay. You mean without any cuts, just really dropping. No, yeah, I think it'd be driven by ISR, FSR, not by vector boson scattering. Yeah, but that's but let's calculate that anyway. So you can also 2021, the paper appeared, we got it out, we had references, and then I had my kid. And those of you who have kids, you know how many hours you spend at night walking back and forth, back and forth, back and forth. Good memories, actually, because I got to. Oh, here or further back? Oh, forward. Tau more here. See, I mean, that's yes, yes. I mean, there's a smiley face. There's a smiley face. Yes. I mean, but this is. I mean, look, okay, the point is, here's numerical evidence. I want analytic. I'm a theorist. I want some analytic formula which actually shows that this isn't, that Higgs is not special. Yeah. But I agree with you, but you're a QCD expert, so all of this is obvious. I agree with you. I completely agree with you. And let's go back to this. Let's start including these order one terms. Let's actually see what these actually look like analytically. And so what we then did was we followed this up by calculating these explicitly in a way that would be applicable for any arbitrary subprocess. And these are what it looks like at leading power. These are the order one terms. The leading power expression for the longitudinally polarized W has a mu-f dependence. If you take it mu-f to be infinity, it vanishes. So this is what it looks like at leading power. But this was also known. I mean, depending on your precise formulation, you know, this is appearing in Sally's paper as well as Dave's paper. But what's newer is what happens when you take this to one order higher consistently. So, oh, I meant to pause this. So ignore the bottom part. So what am I doing? So this just to take one step back. I'm keeping track of these terms. So what's funny is that there's a lot of rich structure. So for example, a left-handed muon radiating a W in the right-handed helicity state next to leading power, the PDF is given by the leading power with a kinematic factor with a helicity flipping term. So that's cool. What's also interesting is that they're negative. Yeah. Now you have to be a little careful because if you just copy and paste what's in Michael's textbook, this William Weizsäcker approximation, he actually makes the Taylor expansion before evaluating the matrix element, which is fine at leading log. That's absolutely fine. But if you keep all the kinematics exact, keep the matrix element exact, square it, then do the Taylor expansion, you get to keep track of these terms a little better. After. Mhm. Yes, they did. They did Taylor expansion. No, that they did a Taylor expansion because if you see at the bottom page of like page 13 or whatever, they say explicitly that they need to do a Taylor expansion in mass over energy. Otherwise, you can't get the longitudinal PDF. They do Taylor expansions or whatever it is. Anyway, it's at the bottom of one of the page. Okay. Anyway, I'm not Sally Dawson. I did not write that paper. So, all right, let's. Okay, so what are the numerical impacts of these corrections? So my point is, these corrections are bad. They're toxic. If you are in a regime in which these order one parameters are becoming relevant, you are not in a regime of the effective W approximation's validity. For example, so here, the solid lines are the leading log approximation PDFs, and you can go to momentum fractions that are arbitrarily low and go to ones that are close to 1. Of course, you get threshold effects if you're a little more careful. But these next to leading power corrections actually have some funny behavior. For example, when the energy, not the Hart scattering scale, but the energy is below this mu-f cutoff, the transverse PDFs go negative. When the energy is below MW, the longitudinal PDF goes negative. And that's a hard cutoff. And that expansion is in Sally's paper. It's also in Dave Soper's paper. So NLP corrections go negative when energy goes below the W mass, which makes sense because you are trying to ask for energy and you don't even have enough energy to make a W on shell, but you've assumed that W is incoming on shell state. All right, so plot that. I'm not sure if we put it into the paper. It might just be in a supplementary material. So what happens if I increase the mu-f to arbitrarily large scales? uh, you have to take a look at the scales that are involved here. So that's 0 to minus 15, that's minus 0.05 to plus 10. So things are not 0, they're just close to 0. And so if we just fix, for example, a momentum fraction be 0.05 at 15 TeV muon energy, you see they're close to 0, and then they are driven negative for large energy. So this is what happens when you start taking mu-f to be above the energy of the W. So what is this telling us? It's telling us that we have analytic evidence of universality, that the effective W approximation is only valid for a particular kinematic regime. You had you had a number of papers that were pointing this out. For example, Roberto and Wutzer pointed this out for a very specific process of vector boson scattering. They're even taking a look at these higher order. You guys estimated what these higher order corrections would look like, but didn't actually write down the formula. Ballestero and company, the Phantom people, also made things, but these were for specific processes. So we now know that this behavior that was seen anecdotally is a little more universally applied. But also, so essentially, you want the vector boson, the incoming vector boson, to carry a large energy in the a protonic center mass frame, and you want it to carry small PT rather than its parent. So I think this is going to earlier what you were saying, Kirill. But then what we did was, just to finish things up, is that we decided to use these pathologies to invert the situation and to sort of guide our phase-space integration and evaluation of the matrix element. So this is a money plot version 2.0. It's no longer on a log scale, it's on a linear scale. And so this is what we have. Again, it's the invariant mass as a function of the Higgs system. And so this purple, so let's see, the blue curve right here, that's a full matrix element. This magenta curve is the previous result. So again, if you start zooming in and if you get really close to, if you get more fine binned and you go from a log plot, linear plot, you see that, in that individual bin, there's a large disagreement. Now, and that's assuming that energy, this is not imposing that the energy has to be larger than the mass requirement. If you impose that, you get rid of all of the soft stuff, the case that are very asymmetric beam configurations in which, one W has a Z of 0.1 and the other W has a Z of 0.10 to the minus 5, these high rapidity asymmetric situations. If you cut out those, you get a leading log approximation that is almost bang on the full matrix element. The leading power, the next to leading power are still large, but that's just saying that these order 1 corrections are still sizable. But as you start going out to larger invariant masses and therefore are pulling more deeply, you're requiring that the incoming W's are more energetic, then you're getting some great agreement within the 10-15% level. And there are not many effective W approximation papers that are able to show agreement with full matrix elements at this level. But okay, let's go back to the statement about what happens if you do much more complicated diagrams, much more complicated processes. Because before, we had chosen large mu-f's, and I think there's been comments about this and suspicions about this. If you choose I think many papers in the past, the effective W approximation has worked by accident because people have been taking mu-f to be too large. So we had these guidance. So let's go to sorry, before I jump to that, here's the rapidity distribution. This is not in the paper, this is newer. So, so here's, again, longitudinal W's to Higgs. So this is the invariant mass of the di-Higgs system. Here's the rapidity without any cuts. And if we then require the invariant mass of the di-Higgs systems to be 1 TeV, there's pretty all right agreement. Okay, so now let's go to money plot number. Why would I want to? It's useless because I'm in the vector boson approximation, so the PT is 0 for the WW system. Oh, internal and Yeah. Right. I wouldn't necessarily say rapidity distribution is suited. You have to actually, invariant mass distribution is one thing. Getting a rapidity distribution of the system, you have to actually be pretty good modeling. So we have the invariant mass distribution and the rapidity. What we're missing is the PT distribution, but you can only get that if you have the Parton shower. Otherwise, we have the core, the PT distribution of the Dihiggs system. But look, momentum conservation, there's no spin correlation, scalars. So we have these internal plots. They're all right. It's all right. All right. So just to finish up, money plot number 2. So guided by the fact that we don't want a super large mu-f, we actually want a small mu-f, which will bring down the cross section. We went back to 3 photons. And so there's a full matrix element. There's leading log. There's leading power. There's next to leading power. It is absolutely terrible agreement. And we hemmed and hawed. And when I was saying that I think previous results for the EWA were accidentally in agreement, it's because the mu-f was ramped up to being to taking on unphysical values. So if we are motivated to have mu-f to be at 450 GeV, because in this case, the PTs of the photons are at 150 GeV. So that means threshold is at 450. And so we took mu-f to be at 450. And this is terrible agreement. But then hemmed and hawed, and thought, well, okay, as was being advocated, there aren't just vector boson scattering diagrams. These are the 12 of the 72 diagrams. These are the VBF topologies, but there are loads. And the way you can actually categorize these is essentially it's a W exchange with 1, 2, or 3 photon ISRs. That's how I think about it. And so what did we do? We actually, so this is QED. I mean, there's still lots of gauge cancellations and all that stuff, but it's QED, so it's a little better understood. And so what we did was, again, something very naive. We took the 2 photon process. So what we did was that we took E mu to 2 photons plus nu and multiplied this by Sudakov factor. Just a QED double log Sudakov factor. And when we added this, bang on. So what I'm calling the Bremsstrahlung, this is the diphoton full matrix element times the Sudakov factor. Adding this because I'm assuming that the third photon is coming from ISR or FSR. And so this would be a factorizable contribution. Yes. On the individual photons. So each photon has to have a PT of 150 GeV. Yes, because you get configurations in which you can have because it's a three body final state, it's possible that you have 2 back-to-back photons and one that is still energetic enough, but relatively collinear. You can have, say, I mean, you can just get these sort of situations because we're dealing with 5 TeV of energy. So in that sense, 150 GeV isn't much. Again, it's naive. It's naive without any fine tuning, without doing a full Partons shower result. But then we get pretty good agreement if we do this. I mean, that it's very naive. For the vector boson topologies, vector boson scattering topologies. Yes. But we're also only at 5 TeV. So all of these other potentially power suppressed terms are still relevant. We're not in a region where we can do a Libby-Sturman analysis and get rid of all of these things. Yeah. So because I'm an academic, I'm curious. If I want to know how to do this. I want to know, when does a W factorize? When does the W emission factorize? So the results are suggesting the following conjecture. When a vector boson carries a large energy in the protonic center mass frame, when it carries a small relative PT in the protonic center mass frame, and these statements, or these are coming from MLM sort of matching arguments, and Tal Han has also made statements on this in his papers very clearly, that when the Mandelstam variables are all comparable in the Hart-Sub process, then what we're seeing is that the full tree level process is a sense can be expressed and approximated to a good degree as a sum of factorized sub processes. And in other words, we're getting to we're starting to see that we're entering a regime in which you have tree level factorization, but this regime is below 10 TeV protonic center of mass energy. And so the final words is that I was motivated by a muon collider, but this actually might be something cool and possibly interesting for the LHC, because I was only but because in order to really trigger this, you need 2-3 TeV, an invariant mass scale of 2-3 TeV. So WW scattering scale of 2-3 TeV in order to start triggering this behavior. And while there's already data in this regime, so it may be possible to already start probing and exploring the formalism, the structure already at the LHC. But you do need more stuff. You need the Parton shower because you have 4 jet tagging. So but we'll see. There are many challenging tasks and questions remaining, but it's clear that there's a clear direction on how to better further develop the theory. So with that, I'll say thank you.
More points to be made? More questions or curiosities for
Oh, I'm afraid of this now.
Actually, I have a question also. But let me start with a comment. So, I'm not quite sure. Well, okay, this is going to be a question. I'm not, I'm not quite sure I understand how you define this next to leading power corrections. Because to properly define next to leading order power corrections, you have to actually work with the full matrix element. They're not coming entirely from the splitting. They're coming from everywhere. And if you do this carefully, either you have to define, start with some operator definition of your PDF, which you don't do, or you have to look at the full matrix element, because there are many sources of these things, okay? So this was the comment. And the question...
I think that's a fair comment. That's also why I want to be clear about what I meant by NLP. I think that's a very fair comment.
Yeah, and I can continue with this comment, because if you really start seriously thinking about these power corrections, your collinear factorization in the normal sense will disappear. Okay?
I'm sorry, say this again.
If you seriously start thinking about these power corrections, your collinear approximation, not collinear approximation, but this factorization into something and something else, it will basically disappear. Okay?
Yeah.
Already at next to leading power.
Yeah.
Now, the question is, okay, we have seen this, in all the previous talks as well. This seems to be a very sophisticated thing that you're trying to do, because, there are many, limits, there are many, configurations, many exceptions. So, you're looking at complicated processes. The question is it really worth it to actually, force these approximations on something that you can calculate exactly?
So I totally sympathize with that. I did this calculation and am of the opinion that you never want to be in a regime in which these corrections become relevant. You want to run away as far away from these corrections as possible, because the leading log approximation factorization, I would expect, I would love to have a factorization theorem that works to arbitrary powers, but I'm sufficiently satisfied with a leading power factorization theorem or a leading power factorization formula. And what I like about this calculation, and I'm very pleased at it, is the unexpected result that the power corrections are negative. And so that means that you start getting very pathological behaviors when you get outside the regimes. When you're in a regime in which these next to leading power corrections or higher power corrections become relevant, things go pathological. So that means you want to get as far away as possible.
Wrong formulas, okay? You're using wrong formulas. These power corrections, they have no meaning that you're showing. Power corrections come from the full matrix element, for which you will not have collinear approximation in that order. I mean, collinear factorization.
Okay, so if
and you see, I'm not even asking about this because this is, at a certain level self-evident. What I'm asking is another thing. So
okay.
You talked about 3-photon production, okay? There are, I don't know how many diagrams, but a large number. And then you're saying there is this vector boson, scattering topologies, VBF topologies, okay? And then there are other topologies. And if you look at the realistic final state, these other topologies, which are characterized by entirely different physics, actually give large contributions.
Yes.
Okay? So you have to be clever one more time. And being clever is a problem for all of us. So you have a MAT graph, put it there, let it run, get the result, everything is fine, everything is correct, nothing is missing. The question is, why is it worth a good idea to pursue this philosophy?
These plots do not go beyond 30 TeV for good reason. They do not go on 30 TeV because we are getting large gauge cancellations. And unless we rewrote MADGraph to be quadruple precision, we are entering a regime in which you are having unphysical gauge contributions, which should cancel, which do cancel. We are getting numerical instabilities. Two people are speaking at once, one at a time.
You're saying this to motivate why doing a calculation with lex will be useful? Why are you mentioning this? My comment is that there is a way to make the full calculation at tree level and also one loop, whatever you want, without encountering this gauge cancellation in the numerical code.
Also change the gauge, absolutely. Go into the axial gauge or this Feynman diagram gauge. You have to do something else though.
I'm saying this can be done, so it's not an obstruction to doing calculation at 10,000 TeV in the electroweak. So it's solved by something else.
There are other ways, absolutely. You can
but they're exact ways. I mean, you just do the same calculation. It's not an approximation.
Oh, sorry. Yes, it's exact. Yes.
Well, I mean, loop, I don't know, but tree level, there are, for example, this 5D gauge that Kaoru, Agivara.
Yeah, that's.
No. Oh, but okay, but this helps. This helps a lot.
I agree.
I mean, the real bottleneck, I think, in this matrix element integration is if you have photons and you want to keep the mass of the muon. So then you have to get the log. And that is the reason why this was the idea of our approach that we proposed. So for the case of the photon, you use the photon PDF because the log are large and also numerically it's a kind of a miracle that you get it correctly, the integration up to the mass of the muon and very energy with the matrix element. And for the others, you use the full matrix element. But my experience so far is that you don't get this large problem of integration, especially because the problem that you claimed is more in the direct production. So when you go
the hard step process.
But if VBF is dominated, as you saw in the bulk on the left, from the like at the threshold you don't have the problem of cancellation that you mentioned. So it's I think I agree with Kirill with the comment.
No, I mean, I think, you know, if you can do the full matrix element, why do an approximation? Sure. But that's not what I'm after. I want to see the W as a parton. That's what I want to see. This is a slightly different approach. This is slightly different argument, motivation. You know, I'm not doing things. I'm not trying to propose using the effective W approximation in lieu of something else. I'm saying that there are two pictures, the full matrix element calculation, in which, because it's electroweak theory, I can, let's just say I can do everything from first principles. And then there's a PDF picture, which says a W can be thought of as a perturbably generated constituent of a muon. I want to see that. That's cool.
So what is for you a definition of a W being a parton and a muon? How you define this?
I mean, I think, I mean, there, in some sense, there's a duality. I mean, if you can redescribe the, you know, what I would like to see and what I think will probably happen is that you'll have some bit of data that describes a process like vector Berlin scattering. And then you'll compare it to the full matrix element, and then you find that, look, this is vector boson scattering. But then you'll have a second theory prediction, which is made of a compendium of the EWA and electroweak showering, and presumably that would reproduce the data to uncertainties. And so I would then say that we can identify that contribution. It would be similar to trying to quantify what is the bottom content of a proton.
Do you always see the bottom as a parton?
That is a process-dependent statement. And a scale-dependent statement, because it's perturbatively generated. I mean, if I put a proton at rest, the bottom content is negligible because the bottom is so far.
No, the LHC. So if you take LHC data, can you describe them, all of them, with the bottom as a parton? No, because in some cases you need like the massive bottom, you need to use it as a fourth level scheme. Like,
Yeah.
and it seems that if in the VBF processes here, you have the similar situation. You
Yeah, but
cannot,
is that a
at these energies,
Is that a problem?
No, but then the question is, okay, we see it, and so next, what do we do?
Oh, as in what's next on the roadmap if we're going to do this?
So what is the conclusion of all of this? Yeah.
Well, the conclusion is that, you know, I don't, the conclusion would be that, but that's some years from now. No, the conclusion is, I will repeat it, is that we're starting to get into, it seems like it seems like we've identified a regime, that I've identified a regime in which things start to factorize at tree level. It's like saying that, you know, you've identified the kinematics and the identified DIS kinematics, and that you start seeing factorization QCD. I mean, it's not a Nobel Prize winning. Well, I'm not saying what I'm doing is Nobel Prize winning, not yet, at least. What I'm saying is that I think we found a regime and some kinematic, rather stringent, but rather simple kinematic criterion, such that you can start seeing factorization in the tree level diagrams. And so if you are satisfying this, then the fragmentation picture should work. Then the you know, then the PDF picture should work. And then you can start putting all these things together. So for me, what I currently have the grant proposal put together to do is to build up the parton shower, the electroweak parton shower with backward evolution. That's next on my personal agenda. There are things like photon Z interference, which I'm interested in understanding more, and I think I have a way to comment on that, but there are several directions to go forward. Yeah.
Maybe it's an obvious comment, but I wanted to say that when you have to do some BSM studies where you need to add effective operators here and there, having some confidence that this thing have been tested and checked in many regimes and understood the problems that can arise and do arise. I'm looking at seeing it's been fighting with some of these problems precisely. I think it's always worth having this picture and exploring. Then that said, for purely standard model processes, you may have alternatives, but I would say that already now we have a bottleneck in doing a full SMEF studies using faster computations like these ones with effective bosons. It's already kind of a computational bottleneck for our poor men without clusters, at least. Or lazy and not clusterized.
Michael?
Actually, I wanted to go in another direction, so maybe you should go forward. Okay.
So I just want to put a quick comment and a quick question on this thing. So comparing the electroweak PDF with the fixed order full matrix element calculation, yes, we can use the Feynman diagram gauge to deal with the gauge cancellation. However, currently there are two problems. One is we don't know how to do the loop calculation if you go with the Feynman diagram gauge. The second one is yeah, okay. So it's not that well. It's not that much easy as in the Feynman gauge. The other one is, I mean, it's not ready for every new physics model, for UE complete model or SMEF model. On the backward, for the EWPDF, of course, also we cannot do we don't know how to do the loop with, I mean, compatible to this PDF. But however, we also need to be careful when studying the new physics things, because if there's.
Fine, hold on. You're saying a lot. Can you take that what did you say that one more time? We don't know how to do what at loop?
Wait, can you use the electroweak PDF with like one loop electroweak correction thing at the?
In Matagraph or
Yeah, in Matagraph. No, yeah, that's what I want to say. Yeah.
Okay, look, if you want to do effective W approximation is already kind of wild and out there.
Mhm.
Now you're proposing to do loop induced maybe, but one loop process on top of something that's wild. I mean, look, we're working hard to add things to Matagraph, but
That's only my minor comment. The major comment is actually as a response to Roberto's just comment is when you are studying SMEF, you should be super careful in using the electroweak PDF, because just in case sometimes, you know, the dimension 6 operator, they give you some contact vertex that doesn't appear in the standard model, and you cannot really do the factorization, so that you may do things wrong.
I'm just seeing.
It's not an unforecastable thing. You know that maybe involve muons, but I think you'll tell us a little of this next week. Will you touch on this next week?
Yeah.
Okay.
Yeah, because you're essentially classifying diagrams that are contrary to Libby-Sturman power counting. That's what's coming. It's down. So if you do the Libby-Sturman sort of organization, they're saying these sort of diagrams are going to be power suppressed. These are going to be factorizable. And if you start introducing arbitrary operators, then in general, you're breaking that classification. Michael?
Okay, so I wanted to ask a different kind of question. So when people talk about an exact matrix element computation in MatGraph, for example, they're talking about something which is very sophisticated, because you have this multi-channel integrator where basically either all Feynman diagrams or all important Feynman diagrams, each one has its own coordinate system. You do integrations over each coordinate system and you put the results together. So the question is it possible to use the effective W, gluon, electron, whatever distributions, the sum of those things as the zeroth order model, and build a better integrator that might make people happier?
I mean, part of this is you don't see that because you're in these factorized pictures, you're assuming that you're treating an intermediate state of a full process to be an
Right.
asymptotic state.
Yes.
And so Matagraph is, I don't know how you would classify that, because then you're saying on the fly, let's take these set of diagrams and treat this as an asymptotic state. And I think
Well, what I'm saying is as a physicist, you look at the diagrams and you identify all the processes, all the channels in which you could potentially apply an effective approximation, effective W, effective photon, etc. And you would give that information to your integrator, as opposed to using the more sophisticated integrator, which is used in MatGraph. And this may be a technical improvement that would allow you to more effectively integrate exact matrix elements. So I'm just asking if that statement is correct or if it's total garbage.
Can I ask ChatGTP or whatever your favorite OpenAI AI program
I'm not
to
going
identify
that far.
these things and to identify on a case-by-case basis regions that might be factorizable? I'm sure you can come up with some algorithm. I mean, that is Libby-Sturman. That is a Libby-Sturman argument. It's like, here's an algorithm to find it.
Yeah.
So I think in principle, someone could be clever enough and say, let's just do this full big thing and decompose it into factorizable channels. And yeah, I'm sure someone clever enough
Right.
can do that. But we
Okay.
need the tools like the Parton shower and fragmentation
But the
function.
question is, if you use that to do the full integral, can you get an advantage from that, as opposed to what's being done now in MatGraph?
It sounds sophisticated, probably. I would say probably. What's up?
So, I mean, when you do the multi-channel Monte Carlo, the question is how much weight you give to the different channels and how you best map the different channels. And if there are topologies that somehow are enhanced by some weak radiation, which is very similar to an enhancement by photon radiation, except that the logarithm is different because the scales are different, then this can be taken care of. And for example, in Wizard, it is taken care of. And yes, you see an improvement in the convergence for this, yes. So this exists. How important this is, I think this has never been really fully quantitatively determined.
So Sherpa does this in reverse. So Sherpa, you stipulate the hard underlying process and then they dress it up with ISR or FSR. So that's kind of the, yeah. Yeah, that's fragmentation. That's a Parton shower picture. That's why I'm pushing for this so much, that you stipulate the underlying hard scattering process and then dress this up with MatGraph plus Parton shower. And then you do this for the other fragmentation processes. Yeah. Thank you.